My name is Justin Cook. I'm aerospace engineering here at Auburn University.
Hey, and I'm Wesley Sellers. I'm also an aerospace engineering student here at Auburn. And today we're going to be talking about our investigation into the auto rotation of Samara seeds. So, just a little bit of an introduction on this experiment. Our goal was to gain a better understanding of how a Samara seed utilizes auto rotation, and we were doing that by applying the theories that we've learned in the Aerodynamics 1 class. So a Samara seed is a fruit that has a airfoil on it that experiences auto rotation that slows its time of descent and also allows it to fall further from the tree, just helping it spread further. And then auto rotation is a rotation caused by air moving around the airfoil. So the Samara seed is actually a very common seed. It comes from about 11 types of trees. So here you can see a diagram of it where it's got the airfoil out to one side with the leading edge sort of more reinforced, and then here we have the wing, and then the seed itself is here in the nut. So our methods for this experiment, we first utilized the Buckingham Pi theorem, which is a key theorem in dimensional analysis. It helps narrow down parameters for the experiment so we don't have to test every single parameter itself. So our main goal is to get an estimate for the time of descent for the Samara seed. So we said the time of descent was a function of the mass of the seed, the chord of the seed, the span of the seed, the density of the air, and the angular velocity of the seed. So after doing our Buckingham Pi analysis, we were left with three pi products. They are pi 1, which is the chord over the span, which is also equal to or 1 over the aspect ratio of the airfoil. We got pi 2, which is the density of the air times the span cubed over the mass of the seed. And then pi 3 was the angular velocity times the time of descent over the span. And as I said earlier, these three pi products were used to narrow down the parameters that need to be tested. And this also allows us to scale this test to a Samara seed of any size. So continuing with our methods, we also use the conservation of momentum integral equation to create an equation for the estimated time of descent. So in the conservation momentum integral equation, we assumed there was no body forces. We also assumed it was steady state. And then we use our control volume, as you can see there, to perform the analysis. And we assumed that the wake of the seed was about twice the diameter. And we said the incoming volume or area was just the size of the diameter or the area of the seed when it was spinning. And once we did the analysis, we ended up with this equation here for the estimated descent time, which was just the height dropped from over the square root of 16 times mass of the seed times gravity over 3 pi times the density of air times the diameter squared. And when we plugged all those variables in, we got an estimated descent time of 15.45 seconds. And then for the experiment itself, 5 seeds were chosen and they were dropped from a height of 17 feet or 5.2 meters. Each seed was dropped 5 times and the descent time was recorded. The seeds were also filmed in slow motion using the slow motion function on an iPhone so that the angular velocity could be calculated. We did that by measuring the time that it took to drop that whole distance and then counting the rotations of the entire descent, and then just did the calculation there. And then for the data collection from the experiment, the seed's descent times were plotted against the assumed variables to understand the relationship between seed characteristics and descent time. We did this so that we could see how a change in one characteristic could affect the descent time. and the pi products were then plotted against pi 3, which had the descent time in it. So it was a non-dimensional value plotted against a non-dimensional value. Because you plot it with a dimensional value, it could cause some experimental error there. And students also created a paper auto-rotating device here. This was just from a simple printout online, folded up and used with a paper clip. We made this device to mimic the descent of the Samara seed using the auto-rotation, and we tested the parameters of characteristics of this one and compared that to that of the seed and to understand the difference between the drops. And we created 5 of these paper devices, and we dropped them from the same height at the same spot and compared the results with those of the smaller seeds.
Okay, and as for our results in this experiment, after completing the calculations, we developed a basis to perform our experiments. The pi products helped narrow down the number of factors that needed to be tested overall. The assumed variables were graphed versus time, and the first 2 pi products were graphed versus the third pi product, which contained the descent time, so that both factors being graphed were non-dimensional overall. The graphs are shown here. So first off, we have mass versus time, and you can see that the results themselves do vary, and they don't really line up with what we previously have predicted or stated. You can move on to that. We have span versus time, chord versus time, angular velocity, surface area, and then like I stated earlier, we have pi 1 versus pi 3, pi 2 versus pi 3. The non-dimensional graphs themselves, they don't really align with our earlier statements and our earlier hypothesis, just due to errors, human error in calculations with the Samara seeds themselves. So these graphs are pretty much all over the place. But with our theory, you can see, especially with span versus time, how one of our heaviest seeds, our largest seeds, had one of the shortest descent times, which doesn't really correlate to everything that we're trying to prove. And just overall, if you just look at the graphs, you can tell that the results vary from seed to seed in different places. With our results, also during the experiment, we decided to test another variable, the surface area of the seed, as can be seen from the graphs. There seems to be a little correlation between the assumed factors and pi products and the descent and the time of descent, which is why the surface area was chosen to be calculated in the first place. The surface area appears to have the most correlation with time of descent, with higher surface areas having higher times of descent. After testing the paper auto-rotating device that Wesley showed you earlier, we compared the times to those of the seeds. The paper devices were found to have much slower times of descent, roughly 1/3 to 1/4 of those of the seeds. And then we determined that it was due to the larger mass and less rigid airfoils on the seeds themselves. The table with the descent times of the paper auto-rotating device is shown here. And as you can see, the times are a lot different from the actual seeds themselves, and that the results also vary. As for our discussion, the Samara seed pictured here, they have unique aerodynamic structures featuring a thin wing that aids in lift generation and dispersal over long distances. The reason why this is because the species of tree that produces these seeds wants to be able to spread out the seeds as far as possible to cover the most amount of area. So if there's a gust of wind, this allows the seed to fly several kilometers away from the host tree where the seed was dropped. And as you can see, the experiment that we conducted aimed to estimate the descent time using thin airfoil theories, but resulted in areas errors due to overlooked variables such as the seed surface area. So we also discovered that the initial assumptions didn't fully capture factors influencing descent time, as was shown in our results through our graphs. This emphasized the importance of thorough experimentation for comprehensive understanding of the tested phenomena. As for our conclusion, to analyze the mechanics and descent duration of the auto-rotating seed, we initially devised two hypothetical assessment methods. First was a Buckingham Pi analysis and a conservation of momentum analysis employing a control volume, as Wesley stated earlier. Following the adjustment of the Buckingham Pi analysis using data derived from experimental analysis, we observed that the drop time exhibited an increase with higher density, radius, spin rate, and chord length, which was to be expected, while conversely decreasing with higher mass and velocity. However, when subjected to the testing involving the repeated dropping of 3 distinct steeds from an elevated position, this equation proved to be an unreliable predictor of real-world drop time. Consequently, the outcomes of this experimental analysis presented notable disparities compared to the conservation of momentum and control volume analysis that we derived earlier, despite subsequent attempts to rectify them retroactively. I would say students understood that there are many factors that affect the Samara seed descent time that must be accounted for in order to fully understand what's going on. Perfect. And these are our references.